we're going to be talking about the properties of logarithms. But before we get there, let's evaluate some logarithms. Make sure you remember how this works. So we're going to look at the log of 125 base 5, and we're going to do these without a calculator. Remember, when we're working with logarithms, we're thinking about exponents. So when you see this, you are thinking, what exponent do I need to put on a base 5 to get 125? And the answer to this question is equal to that logarithm. So we know that 5 cubed is 125, so our answer to this is 3. So let's do our next one. The log of 16 base 2. So again, I'm thinking 2 to what power would give me 16? And we know 2 times 2 times 2 times 2. I don't remember how many 2's I said. We should have 4 factors of 2 that would give us 16. So we know the answer there is 4. Remember that this is our common logarithm because we don't see a base. We know that base is 10. And so again, the question is 10 to what power gives you 100,000? And we know that 10 to the 5th power would give us that 100,000. Notice we have 5 zeros there. So our answer is 5. And I hope this one is not too bad for you. Notice I wouldn't even need to write the equation. 3 to what power would give you 3? Well, we know it's 3 to the 1st power equals 3. So I just wanted to start with those logarithm questions. Let's do a few more. I have a few problems that we're going to do where we're going to evaluate some logarithms and take their sum. So let's roll through these. The log of 5 base 5, just like our previous one where we had the log of 3 base 3, we know we raise 5 to the 1st power to get 5. So our answer is 1. Again, we're thinking exponents. When we're thinking about logarithms, we're thinking about exponents. Let's see if we can get this one then. What exponent do you need to put on a 5 to get 25? We know it's 5 squared, so our answer is 2. And we're just taking the sum of those. We have 1 plus 2, that's 3. Let's do the next one. We have the log of 8 base 2. So what exponent do we need to put on a 2 to get 8? We know it's 2 to the 3rd power that is 8, so our result there is 3. The log of 2 base 2 is just a 1, so our sum is 4. 4. Let's see, our next one, log of 100 base 10. This is an interesting one. We know that 10 squared is 100. For whatever reason, I frequently have people put an answer of 10 for this one because they're thinking 10 times 10 is 100. So they write a 10 there. But we know it's the exponent. Keep in mind when we're working with logarithms, we're thinking about the exponent. It's 10 squared that is 100, so our result is 2. Similarly, 10 cubed is 1,000, so we would get 3, and our result is 5. And let's look at this last one. We have the log of 9 base 3. We know that's 2. And I tossed this one in for good measure. Log of 1/3 base 3. What exponent do you have to put on a 3 to get 1/3? Notice that we need to drop it to the denominator. That implies we have a negative exponent. So it's actually a -1. So if we do that addition or subtraction, we would get 1. So we have calculated those sums. Now I want to bring back the paper that we just did. Let's look at this. Let me slide it in here. Let's see if we can squeeze it in. Can we still see it? I want you to see that we have the log of 5 base 5. The log of 25 base 5 was equal to 3. And the log of 125 was also equal to 3. These two were equal. These two expressions were both equal to 4. These two expressions were both equal to 5. And these two expressions were both equal to 1. Let me slide them a little bit closer so we can see. And what we see is this. The log of 5 base 5 plus the log of 25 base 5 is equal to the log of 125 base 5. Those two things are equal. And notice 5 times 25 is equal to 125. Let's look at this problem. We have the log of 8 base 2 plus the log of 2 base 2 equals the log of 16 base 2. And notice 8 times 2 is 16. Similarly here, these two quantities were equal. And we have 100 times 1,000 equals 100,000. And last, I have this one. The log of 9 plus the log of 1/3 equals the log of 3. And we know 9 times 1/3 equals 3. Now, this doesn't prove anything, but it does strongly suggest this property of logarithms, that if you have the sum of two logs, the log of m plus the log of n, it would equal the log of their product. Remember, it was not the sum. This is the part that sometimes people find surprising. We take their product. 8 times 2 is 16. So it's the log of m times n, keeping the base the same, whatever that base might be. That's our big first property of logarithms that I wanted to mention. Now, here's what it's related to. I'm not going to prove it to you, but I want to show you what it's related to. Because when we're thinking about logarithms, we're thinking about exponents. They're related to exponents, and their properties are related to the properties of exponents. And let me show you what I mean. In algebra, we're familiar, I hope you're familiar with this. If you have x to the 3rd times x to the 11th, we know that the product of x to the 3rd times x to the 11th is x to the 14th. So we know already, based on our study in algebra, that there's a relationship between multiplication and an addition of exponents. And that's what this property is related to. And in fact, we have a corresponding property in algebra. You know this one. If you have x to the 20th divided by x to the 3, do you remember what you do with the exponents? You subtract them. We would get x to the 17th. So we remember that there's a relationship between division, when you have the same base and you have exponents, and subtraction of those exponents. And that brings me to our second property of logarithms, and I'm going to move this one over and you can see the properties officially. This is property 1. I just rewrote it in the other order. It doesn't matter. This equation works in both directions. You can start with the log of a product. We say that the log of a product equals the sum of two logs. But you could take the sum of two logs and write it as the log of the product. And we have the log of a quotient equals the difference of those logs. This does assume that m and n and a, each of these quantities, are positive real numbers. Remember, we're not taking logs of negative numbers. We force them to be positive, so we can only expand it in this way if these are known to be positive. And we don't let the base for a logarithm equal 1. So let's practice using these properties with some problems. So we have the log of x base 5 equals the log of x base 5. Or excuse me, equals log of x base 5 plus the log of x base 5 equals, we use that first big property that says We have the sum of two logs. It's equal to the log of their product. So I make sure I multiply those together. It is so tempting when people are first learning to work with logarithms to add them, but it is a product. And that one's finished. And let's move on to this one. We have the difference between two logs. Notice the bases are the same as they were here. This happens to be base 10. But now we have the difference between two logs, so we know the result is going to be the log, a single log of their quotient. And I know the first argument right here will go in the numerator, and this second one will go in the denominator. So we have the log of 23 over x plus 2. And it is okay to write it that way. Sometimes for clarity, people write parentheses around it, so it's very, very clear it's the log of that single fraction. Let's do another one. Suppose the directions here said to simplify. Oh, and we can't use a calculator. If we started to try to evaluate this one, the log of 40 base 2, notice that isn't one that we'd be familiar with. I don't know what exponent I'd have to raise 2 to to get 40. 2 to what power is 40? I don't know the answer to that. But I do know I can use my property of the logs that says the difference between two logs, or the difference of the logs, is the log of their quotient. So I know that's the log of 40 over 5, keeping the base the same. But 40 over 5 is just 8. And I know how to evaluate that. We know that 2 to the third power is 8, so we would simplify it and make it 3. Let's do the next one. Again, individually, I don't know what these are. The log of 2 base 6, I don't know what that value is, and I don't know the value of this one either. But I do know that I can combine them. I know it's the log of the product of 2 times 18. And I know that 2 times 18 is 36. So it boils down to the log of 36 base 6. What exponent do I need to put on a 6 to get 36? And we know that's just a 2. Let's look at this problem. The log of x to the third power. Now, I didn't tell you what to do with it. I just wanted you to consider it. And we know that x cubed is x times x times x. So let's just rewrite it that way. Log of x cubed is the log of x times x times x. Well, we can apply big property number 1 right here a couple of times to get this. I'll just expand it all in one fell swoop. And we know that we have the sum of some logs. So I would have the log of x plus the log of x plus the log of x. Because the log of a product equals the sum of the logs. And then let's finish. We have 1 log x plus 1 log x plus 1 log x. That gives us 3 log x. So now look at what this equation tells us. It tells us that the log of x cubed actually equals 3 times the log of x. Again, this doesn't prove anything, but it suggests our third big property of logarithms, and that is the log of a power equals the product of the power and the log. And this represents an example of our third property that I'm going to write right here. We have these 3 big properties of logarithms that often get written together. So here it is. It's the log of m raised to a power, keeping the base the same. And r can be any real number. and we bring the r in front and multiply it by the log of m base a. And it looks like that. Let's practice writing as a single log, now adding this to our repertoire of properties we're familiar with. So, the directions are to write as a single logarithm. Let's do this one first. So we have a coefficient of our logarithm. Remember, as with the previous properties, you can go in either direction. So I can start with the log of a power and write it as the product of the power and the log. Or if I have the product of a power and a log, I can rewrite it this way. So that's what I'm going to do. Here, I see 2 times ln of x. I'm going to bring that coefficient up as the exponent. So I would have ln of x squared. And there's just a coefficient of 1. There's a negative there, but I'm not going to do anything with that at this moment. So I've taken care of this coefficient of 2. And now I have 2 logarithms with the same base. I can use our second property that says when you have the difference between 2 logs, it's the log of their quotient. And I would have the natural log of x squared over y, and it's finished. Let's move on to this one. Let's handle it the same way. The coefficients go up as the exponent, that power. So I would have the log of x cubed plus the log of, and I'm about to write y to the 1/2, right? We know that's y to the 1/2, but let me remind you that y to the 1/2 is equivalent to the square root of y. So I'm just going to write it as the square root of y. I just want you to see this idea enough that it is no big deal to you, whether we write an expression with an exponent of 1/2 or we write it with the square root. Now let's put these together. We have the sum of 2 logs. We know the result will be the log of their product. So we have x cubed times the square root of y. Notice right here I used the natural log. Don't forget that's base e. And over here we used the common log. Right. Didn't really change or affect what we did in the problem, but I just wanted you to see that and remind you that this is base e and this is base 10. Let's do another one. Suppose we have this problem to write as a single logarithm. We can handle it the same way. We have coefficients that aren't 1, so we're going to make those become powers or exponents. So we have this 1/4. It's going to become my exponent, but I'm going to write it as a radical, just like I did on the previous one. Remember, a 1/4 exponent is equivalent to a 4th root. So let me write it that way, 4th root of a plus 2. Just good for us to keep in mind the 1/4 exponent is equivalent to a 4th root. Minus, and now my coefficient here of 5 is going up as my exponent, log of b to the 5th, keeping my base the same. Notice I do have the same base on each of these. So I have the log of, I have a difference between 2 logs, so make sure I write it as the log of the quotient. Oop, I almost left off the base. The base is 7. I have a quotient of the 4th root of a plus 2 divided by b to the 5th power. I want to show you one more thing. One other idea that ties a few things together. Suppose we're doing this one right as a single logarithm. I could handle it just the same way we did the previous problem, but I want to show you something just a little bit different. On this problem, I could take the 4 up as the exponent, so let's do that. The log of x to the 4th. And on this one, in the previous example, I put the 3 up as the exponent. You could, in fact, take the entire -3. In fact, I'm thinking of this as plus a -3. This way is what I'm thinking. So it becomes plus the log of y to the -3rd power. Now I see this addition here, so I put those together with a product. So I have the log of x to the 4th, y to the -3. But as you know, a negative exponent implies it could be moved to the denominator and changed to a positive exponent, and we have the log of x to the 4th over y cubed. Now I wanted to show you all of this detail because here's what I wanted to get to. The fact that when you have, I wish I hadn't changed the original problem, it was 4 log x minus 3 log y. When you see a term that is preceded with a negative, we expect it to go to the denominator in your result. In fact, let's look at this one. Let's condense it or write it as a single logarithm. I'm going to take care of all of the exponents, and I'm going to use the negatives as exponents, as part of the exponent. So I'd have log of a to the 7th plus the log of b to the 2nd plus the log of c to the -4th plus the log of d to the -3rd plus the log of e. Now when I put these together, I have just the sum. So I'm putting it together as the log of a product. I just have a product of 5 expressions. A to the 7th, b to the 2nd, c to the -4th, d to the -3rd, e to the 1st. And when I rewrite this, taking care of my negative exponents, we know that means those terms go to the denominator. I would have the log of a to the 7th, b to the 2nd. These are going to the denominator. I'll keep my e in the numerator. Divided by c to the 4th, d to the 3rd. And I have it done. Now with practice, what you can find is that you can move straight from here to here, recognizing that the coefficient will become your exponent. The 2 became the exponent, and if the coefficient is negative, you make sure it goes to the denominator. But you don't have to go straight from here to here now. That's with practice. Let me put parentheses around it just for clarity. But I just wanted to show you that so you can see that that negative in front of the expression will mean the argument. That piece right here will go to the denominator. Now I hope you'll go practice with your properties of logarithms.